So students tend to struggle with piecewise functions. This first piecewise function we're actually going to draw. Now, I promised you that I was never going to give you like crazy functions in here. We're going to keep the functions themselves simple, just so that you can show me that you get the hang of graphing with different pieces. So what we do is we make a table of values. Sorry, I didn't leave myself a ton of room here, so I'm going to put my table of values right here, and I'm going to put 4 on there twice. Wherever the function changes, put that value on twice. One will be an open circle, one will be a closed circle, right? This equal to sign dictates that the circle is closed. Then, I mean, this function we know is linear. Only takes 2 points to determine that it's, determine a line. I'll put 3 on, and then put a few points here, but actually this second function's awfully easy, right? When x is greater than or equal to 4, my function is constant, 1, 1, 1, no matter what. So I'm going to put a closed dot here at 4 and get my line tool. And so that's just a horizontal line, and then I would put a arrow on the end of that, okay, to show that that continues indefinitely because x is greater than 4 all the way to the right. Okay, now for this other piece of the function, let's see, that's 12 minus 5 is 7, and then plug in 3. 9 minus that is 4, right? The slope is 3. We can see it going down by 3s. Right? This one would be my open circle up here at 7. Okay, so if this is 7, I have an open circle here. And let's see, at 2, I should be at 1. So halfway between 0 and 4, I should be at 1. So it takes 2 points to determine a line. Let me select my line tool so I can actually make a straight line. And let's see, this thing has a y-intercept at -5, so kind of like down there. Okay, and so now we're looking for limits from the left and from the right. What I want you to notice, because in the next example, I'm going to suggest that we don't even draw it. Okay, but look right here, right? I don't even have to have the picture to say that as I come from the left, right, on the left-hand side, I am going to see values getting closer to 7. And on the right-hand side, I'm getting values closer to 1. Okay, therefore, limit does not exist. Okay, and so our reason for discontinuity, remember we had those 3 reasons. 1 was the function had to be defined. 2 was that the limit had to exist. And 3 was that the limit had to equal the functional value. Okay, so obviously here when I say why is this function discontinuous at 2, functional value does exist, right? F of 4 is 1, I'm sorry, is 1. The closed circle is the functional value. So here I would say reason for discontinuity, the limit does not exist at 4. Okay, now the next example I'm going to tell you not to draw. Okay, because we can see the answer to the limits just by looking at the table. Okay, the limit to the left will be the first one, right, where we're looking at the values less than 4, the number x, so in this case 4, and the limit from the right will be the second number. Okay, so if we think of terms of going in order, right, so starting here, the only thing I'm going to put on my table is -3 twice. Okay, and if I look at the function where we're less than -3, right, and there would be an open circle there, but I get 3, which means that's the limit from the left. That's when I'm a little bit less than 3, I would get this limit of 3. Okay, so you try, pause the video for a minute. We're going to put 2 on here, so we're not doing any other values. This is all we're going to look at in the table. So find these, either this would be a whole, right, which we really don't care because when it's limit, we don't care if it's a closed circle or an open circle, right? That would be a whole because it's less than. This would be the functional value right here, but again, that doesn't matter when it comes to limit. So pause the video and you try this. Okay, so if you're back, I plugged in here, and this would be my limit to the right, because this will be for values greater than or equal to -3, which means, of course, this limit DNE, right, because the left and right don't match. Now, when I plug in 2, I notice that I get 4, right, which means one function, and I get 4 here. When I look at x squared, I also get 4, which means that one function picks up where the other function left off. Okay, so if I asked you about discontinuities, right, this function here is continuous at x equals 4. The limit equals the functional value. Okay, one piece of the curve picks up where the other left off. Okay, this function is discontinuous at x equals -3 since the limit, that's condition 2, limit DNE. Okay, so if all I'm asking you for is limits and points of discontinuity, and I don't make you draw it, right? You don't have to draw it all the way out. Okay, so again, thanks for watching. I hope this helped.